So for chapter 7, we're going to talk about applications of integration. And for section 7.1, we want to talk about the area of a region between two curves. And so we already know that integration or integrals of a curve just represent the area below the curve, right? So if we have, say we have some kind of curve that looks like this, then the integral will just give us, whatever area falls below it based on our limits. Well, now if we are given two curves, and curves just really means just given two graphs, right? Because it could be a line, so it doesn't necessarily have to be a curve. But if we are given two curves, so maybe something that looks like this. So we have this, and then we have this. And what we want to find is the area that is between those two curves. Okay, and I'm going to call this top curve F, and then I'm going to call the upside down or the bottom one G. Okay, and so how this works with integration is to find the area between these 2 points. We just take the integral, but we have to find these intersection points because our area is limited between those 2 points. And we call those points A and B, usually with A being on the left, and then B being on the right. Doesn't have to be, whatever you want to call it, but A and B is normally the setup. And so what is happening is, and let me draw this a little better up here just so you can kind of see where this comes from. So let's say that we have this and this, okay? So we know that the area of under F is represented by the integral of this, okay? Well, the area under G is represented by this. So what we are really doing is finding the area under F and subtracting off the area under G to leave us this middle portion. Okay? And so how we do that is by integration, by saying from A to B, we evaluate the integral of F, we'll say F of X, minus G of X with respect to X. Okay? You can find these sometimes by graphing the limits. You may have to do some algebra, and we'll talk about both of those. But let's do an example here. So let's say that example 1, let's say that we're given the two curves y1 equals x squared minus 9x, and y2 is equal to 0. All right. A lot of the homework questions shows you the graph, but you may have to graph it yourself. And what this looks like, x squared minus 9x looks something like that, with 9 being right there. So this is, we'll say this is y1. y2 being 0, it just goes across the x-axis. So here is y2. So what we're trying to find is the curve between the two, or the area between the two curves. So we're trying to find this area here. All right. Well, my A is going to be 0, B is going to be 9, because that's my two intersection points at 0 and 9. All right. And so I do the integral from 0 to 9 of the top curve. Well, here my top curve is 0 minus my bottom curve, which is x squared minus 9x. And I'm just going to integrate that and evaluate with respect to x. Okay. So just rewriting this with distributing that negative, that's negative x squared minus 9 or plus 9x dx. Now I just do the integration, and so I get negative x cubed over 3 plus 9x squared divided by 2. And I don't have to pick up plus c because I have defined limits. And then I just plug in my upper limit and subtract my lower limit. Well, of course, my lower limit here is 0, so I'm just going to plug in 9. Over 2. Evaluate it, and I get 243 over 2, which is really like 121.5. So the area that is under that curve is equal to, or between those two curves, is equal to 243 divided by 2. So that is how that works. Okay. To show you another example, what if we are given two curves that have the same overlap? Or multiple overlaps, I should say. So let's say f of x is equal to x to the 5th plus 2. G of x is equal to x plus 2. All right, and then just to give a rough sketch, all right, so g of x plus 2 looks something like this, 2 being right there. F of x is going to look something like this. Yeah. So g of x is the line, f of x is the curve, and that's not a great drawing, but it's good enough because what we're going to look at is the areas here. All right. So I need to find these intersection points. So my intersection points, I can find that by just setting them equal to one another. So x to the 5th plus 2 equals x plus 2. All right. I subtract 2 over, I get that x to the 5th is equal to x. Well, I already know, and by looking at it, I can tell too, right? One of my values is going to be x is 0. All right. And ever how you want to go about solving this is fine. I'm just going to divide by x and just say x to the 4th is equal to 1. Take the 4th root of that, 1, and you get plus or minus 1. So my values are going to be -1, 0, and 1. All right. So here's my -1, here's 0, here's 1. Notice these values are always on the x-axis, similar to when we do any kind of integration. All right. But what I have now is I have two areas. Okay. So I need to add those areas together. And so what I'm going to say is from -1 to 0, my f of x was on top. So I have x to the 5th plus 2 minus x plus 2 with respect to x. And then I'm going to add that second area. Well, that second area runs from 0 to 1. But g of x is now on top, so I have x plus 2 minus x to the 5th plus 2 dx. And then I would just go through the integration methods, okay? So the thing is, it's always top curve minus bottom curve, but we want to make sure that we encompass the entire area, okay? There will be some examples where you will just be given points, and you have to connect those points, develop the lines or the equations that go through those points, and a few different things like that, but that's more algebra. And so then the last thing I want to make a note of, so on a similar note to what we are already doing, if we are given vertical curves, I'm going to put vertical in quotes there because it's not really proper, but vertical curves, like let's say we have something that looks like, let's say we have x equals y squared plus 1, which looks something like this. Okay. And then we have x equals negative y to the 4th plus 3. It's going to look something like this, right? then we can integrate this the same way, and we still do, we call the top D and C, except now we look at this, our right curve, first as our top curve. Because if we were to rotate this over, what we're really finding is the area between here and the y-axis. Okay? So the right curve would be on top. So our limits or whatever, they're C and D. But our right curve would be the negative y plus 3, negative y to the fourth plus 3, minus y squared plus 1 with respect to y. Okay. So you would integrate that based on whatever the points are if you are given kind of that vertical overlap. All right. So this finishes up section 7.1. As always, feel free to email me if you have any questions, and have a great rest of your day.